Hello, everyone. My name is Nirbhay, and I'm from NIT Tiruchirapalli, India. And I came yesterday only here to present my research on the mechanical properties and chloride penetration resistance studies on fiber-reinforced semi-lightweight concrete. I know the name is quite big, but the research is also quite big. It starts in three parts. Like first was the identification of the materials, what we are going to use to make the lightweight aggregates we are going to use. We are not using the traditional or the conventional aggregates we use in the cement, like the concrete. We have made them ourselves in our labs, the aggregates we are using. Second is we wanted to make it a lightweight, but based on our results, it came to be a semi-lightweight. The third things are the tests we did on the concrete, that are the mechanical properties and chloride penetration resistance studies. Okay. I think we are very clear with what is a fiber-reinforced concrete. There are basically three types, like the lightweight aggregate, aerated, and the no-fines. We are working on the lightweight aggregate concrete. And the lightweight aggregate concrete we are using are made using the aggregates we have made ourselves. The second thing important in our study was the pelletizer we used to make the aggregates. Now, what is important in that is the thing you are seeing on your right, the angle we need to put upon the amount of materials we need to use in it was the major task or the major problem in that, or we can say the major challenge in that. Second is the process we use for making the aggregates. There are two processes, cold bonded and sintering process. Cold bonded is making aggregates in the pelletizer and then putting them in the sunlight to get them dried. The second is sintering process, which is making them heat in a kiln, which is more than 1000 degrees Celsius, and getting the proper size. Now, what is the need of this study, or like why we went with this is, like there are very less number of studies done on the lightweight aggregates concrete, especially on artificial aggregates, which we prepare ourselves. I'll be continuing for that, how we did that. Now, coming to our objectives. First, we'll study the fresh and hardened properties of the concrete. Then we also did the durability test using water absorption, sorptivity, ultrasonic pulse velocity test, and electrical resistivity. Then we did the chloride penetration resistance studies based upon rapid chloride permeability test, we say RCPT. At the last, we also did the cost benefits of the concrete we prepared, and we'll be discussing in the later slides. Now, let's come to this slide. Yeah. First is identification of potential sustainable material. Now, near our institute, there are a lot of factories which produces a lot of wood ash. Now, we identified that in the wood ash, there is a lot of calcium, especially in the leaves of tamarind. When they're burnt, we get a lot of calcium content in that. We did the XRF analysis on that, and we found various properties of calcium found in that product. So we named it as calcite powder. And there are like tons of waste available for this thing, so we use this as a major component. Second was the PET fiber we get from the plastic bottles, and we will be using that as a fiber for enhancing the tensile properties of our concrete. Now coming to the interesting part, how we prepare that pellets, or we say the aggregates we used in our concrete. Now you can see the like the pictures on your right. The pelletizer use the angle, the RPM, how much time we have to give to get the proper shape, or the size we require for our concrete was very important in that. So the major components were calcite powder, class F fly ash, and cement, and a small amount of a little, like we say, stone chips. Now, how much quantity we needed for that? So we took around 300 kgs of, we made 300 kgs of pellets, because we had a lot amount of sample size we need to prepare for our test. So we used that thing, and you can see how angular shapes, we can get different types of shapes depending upon the angle of the pelletizer. So the optimum angle was 54 degrees, where we got the proper amount, size of aggregates and the shape of aggregates we need to get for our concrete. Second was preparing of the PET fibers. You can also see the customized tool we made in our lab only, to cut the PET bottle fibers. We don't want to put like cost on like getting cutters for like the plastic things. So we took the waste plastic bottles available in our college campus. We washed them properly and we used this tool and we cut them. Like the major challenge in this plastic was getting the aspect ratio, because aspect ratios plays a very important role in the bonding of the concrete when we get the final results. So the width and the length which was decided was 5 mm and 25 mm was the length. And we got like the fibers you can see on your right. Now coming to the design part, like what was the design mix or how many samples we took. So it was a long process of 3 months. Yeah, to be like very approximate, 3 months. Like first of all, we have to decide how much coarse aggregate or like what are the sizes of coarse aggregate we have to take. So we took like help from the ASTM C330 code, and we prepared 3 samples in which like they were divided into 10 to 20 mm and 4.7 to 10 mm, like 50-50 percentage, 70-30 percentage, and 90-10 percentage. And the optimum percentage was found to be 50-50 percentage, in which we got the highest compressive strength and the most workability at the 7th day. So we proceeded with that sample. Second major challenge was deciding the optimum fiber content. So we decided the 4 different samples, starting from 0.25% to 1% with the increment of 0.25% each. And these were the samples we took and the different tests we conducted on our specimens. Yeah. Now you can see the first figure shows the split tensile strength test. The very first figure shows the conventional, like without fiber reinforced in that. We can see a proper failure. But the picture down to that, there's a proper hairline crack, but it is not fully breakable, which shows the fiber imparted the ductility in that and also improved the strength of the like our sample. On the right, you can see the shear strength, flexural strength test. In that also, the first sample is the sample without fiber. It breaks like from the center. And the second one, the sample shows the FR concrete, like the fiber reinforced, which shows it doesn't break fully, imparting ductility and tensile properties in that, which was our major objective of imparting in the samples. Now seeing the results, the first major impact was the density, which was our objective of getting semi-lightweight. We got it in the range of 1996 to 2121. The conventional concrete, as you all know, it's around 2400 kg meter cube. We have reduced around 300 kg per meter cube the density, which is a huge chunk. Second was like with increase in fiber content in the samples, we saw a decrease in the slump value, but it was also a moderate slump value, which is workable for which is a good workable concrete. Coming to the compressive strength was same in all the samples. We didn't see a marginal increase in all. But if we see the shear strength and the flexural strength, there was a marginal increase in those factors. And we also saw the electrical resistivity and the sorptivity test. There was a huge increase in that with the introduction of fiber. Next is the cost analysis of the materials. If we see a conventional concrete, we get a cost of 4,400. That value is in INR, not US dollars. So the conventional cost is 4,400 per kg of concrete. But if we use the fiber reinforced semi-lightweight concrete, the cost came to be 4,100, which reduces around 7 to 8% of the total cost if we see in the batch. Coming to the conclusions, the 50-50% introduction of coarse aggregate was found to be the optimum one, and fiber reinforced with 0.5% PET fibers was found to be the most optimal specimen. If we talk about compressive strength, there was a slight reduce with introduction of fibers, but that also we can say it was due to the not proper bonding. We found that the shear strength was increased, and also the other durability parameters like RCPT test, Sorptivity, and UPB test increased with increase in the fiber content, which is a good thing. And At last, the electrical resistivity also increased with the introduction of PET fibers, and that's it.